Hello, we are discussing about third part of sampling gates under pulse and digital circuits. So till now we have seen about the unidirectional diode sampling gates, and that can be extended to more number of inputs, their advantage and disadvantage. Later we have seen about the bidirectional sampling gates using BJTs, okay, by using a single transistor, by going through emitter coupled BJT. And next we observed that when there is a pedestal occurs in both cases, and afterwards we have seen how to remove the pedestal and what are the disadvantages of that circuit which can remove the pedestal. Now we are moving into the bidirectional sampling gate using diodes. Look at the circuit. The circuit is a bidirectional sampling gate using diodes. So there are two diodes we are using, D1 and D2, and two control signals it requires. Both the control signals are going to be exactly opposite of each other, where the source signal is going to be applied to both commonly. So a common source signal is applied to both the diodes, but control signals are going to be applied to each diode. But remember that one, the control signals are going to be exactly opposite of each other. Okay, so like this, if during any instant of time, if one of the Vc is at plus Vc, then the other will be at minus Vc. If one of the voltage is at plus Vn, the other will be at minus Vn. Okay, that means at any instant of time you are applying same voltage, but for D1 it is positively applied and for D2 it is negatively applied. Otherwise, for D1, if you are applying negative voltage, the same amount of positive voltage are applying for the D2. Okay. Generally, diode sampling gates are going to preferred over sampling gates using BJTs because it has two advantages. First advantage is nothing but linearity in the operation. Output is more linearly related to inputs. First one. And second advantage is the diode sampling gates can be easily adjusted to get the zero pedestal. It is easy to adjust the zero pedestal when the sampling gate is using diodes. So these are the two basic advantages. That's why sampling gates are going to be preferred using with diodes. Now we'll see bidirectional diode sampling gate, its operation, okay, and how much is going to be the gain and what must be the minimum signals. Okay. Now we'll discuss about operation. Let case 1, when Vc of D1 is going to be Vc of D1, okay, Vc of D1, that is this point, is at Vc, that is plus Vc, that is positive voltage, and by that time Vc of D2 will be at minus Vc. Then what happens to the diode? Now look at this one. Diode N side, D1 N side is connected to ground, whereas P side is connecting with more positive voltage, that is plus Vc. And D2 is going to, P side is connecting with 0 and N side is connecting with a large negative voltage, that is minus Vc. Both the voltages are going to be same. You can observe that one. So that means D1 is forward bias and D2 is also forward bias. Both are going to be having same forward bias. So that is both the diodes are forward biased by the same amount. So they act as short circuits. When they act as short circuit, by that time V0 is proportional to Vs. So this is called as transmission period. During the transmission period, V0 is proportional to Vs. What will be the voltage? So what is voltage when Vs is equal to 0? If input signal is not applied, then what is the output voltage of this circuit during transmission period? Okay, if you apply input voltage, then output is proportional to Vs. Now if the input signal is not applied, that is Vs is 0, then what will be the output voltage? Because you are applying control voltage, that is one is plus Vc, the other is minus Vc. What can be the output you can expect? So here the answer is V0 is equal to 0 volts. Why? This you can easily find. Whenever the input signal is 0, look at this one. If you are not applying any input signal, then the node P is going to be applied with point A. Both are going to be same because diode is forward bias. This diode is also forward bias. So simply replace the diode symbol with short circuit. Then point A is also connecting to P. Point B is also connecting to P. Point A is with plus Vc voltage, that is positive voltage is going to be connecting at P, and the same amount of negative voltage is connecting at P through B. So both the voltages are going to be applied at same point. So they may added up, that is superposition theorem, so that plus Vc and minus Vc, they will be added up each other. So you are going to get 0 voltage effectively. So V0 is equal to 0. That is the reason why we are going for the same amount of voltage during the at any instant of time, plus Vc and minus Vc. Plus Vc minus Vc get cancels, so that at node P you will get 0 voltage. That means you can get 0 pedestal. 0 pedestal. Now, so that implies nothing but from this one, if Vs is applied, then that Vs is going to be passing through D1 as well as D2. In both ways, Vs is going to be connecting to V0. So V0 is only function of Vs. At present, what we can conclude is V0 is only function of Vs, because at any instant of time the node P is going to be node P is supplied with same amount of positive and negative voltage. That's why effective voltage with respect to control voltage is 0 at the output node. Now second case. When Vc of D1 is at minus Vn and Vc of D2 is at plus Vn, that means you are applying negative voltage towards diode D1 and positive voltage towards diode D2 inside. Then both the diodes D1 and D2 will be reverse bias and acts as open circuits. When they act as open circuit, simply you remove those diodes. Whenever they are removed or they are replaced with open circuit, then V0 is equal to 0 as there is no current flows in the load resistor. That means V0 is independent of inputs, independent of Vs. So this is called as non-transmission period. So during non-transmission period, V0 is independent of input and V0 is 0. During transmission period, V0 is proportional to Vs if Vs is applied. Otherwise, V0 is 0 when Vs is 0. That means 0 pedestal. Already we have seen pedestal is the difference in the output voltage when compared with during transmission with 0 input signal and during non-transmission period. If there is a difference, then it is called as pedestal is present. If there is no difference between these two cases, then no pedestal. So this is what we can see the operation. And now we are going to calculate how much of input signal is going to be appeared at the output side. That means gain. Gain of this circuit. Gain of this circuit is nothing but output voltage by input voltage. So how much is the gain of this circuit? And during transmission period, we know that one. During transmission period, D1 and D2 are forward bias. So you are applying Vc is equal to Okay, control voltage is Vc we are going with. Some Vc, that is positive voltage. What must be the minimum positive voltage you must apply? Minimum positive voltage to be applied at D1. That means the same amount of negative voltage you are applying towards D2. Okay, so what must be the Vc minimum to be applied across D1 so that both the diodes are forward bias, none of it going into reverse bias. And third case, during non-transmission period, both the diodes are reverse bias. So to keep both the diodes in reverse bias condition, what must be the minimum signal? That is, what is the value of Vn minimum? We will always consider only positive magnitude. That is minimum positive voltage. To be applied to D2. Remember this one. For D2 we are applying positive Vn. So not to get confusion, if you are going to consider that Vn towards D1, that is negative, always in your mind you should remember that one, there is a negative voltage, Vn is negative, but it is not the case. So we are going to consider for Vc minimum. Okay, in case of reverse bias diodes we are going for the positive polarity, that is applying to D2, and in case of forward bias, positive polarity only we are considering for the control voltage, that is what you are applying towards D1. So these are the three cases we are going to discuss. Okay, because within these limits only it can act as bidirectional sampling gate, even though the signal is going to be Vs is okay either positive or negative, output is going to be proportional to Vs. Okay. And you may think that one depending on these diode directions, okay, it can also accept positive as well as negative signals. Okay, since the voltage what we are taking zero reference is this one, Vn is a large positive voltage, Vc is a large negative voltage. Okay, so for positive voltages, okay, it can be passed through D1, you can think, and for negative voltage the signal is going to be passing through D2 and it reaches the output. So the circuit is going to be looks like bidirectional. It can also pass positive going signals as well as negative going signals. So this is a bidirectional sampling gate using diodes. Now we are going to calculate these three parameters: gain, Vc minimum and Vn minimum. Okay. So first we will draw the equivalent circuit, and from that one we will write the Thevenin's equivalent. Okay, then you are going to calculate the relation between output and input, that means gain. Okay, this is the equivalent circuit. Look at this one. This is the equivalent circuit. Okay, this is the given circuit of bidirectional diode sampling gate, and that can be redrawn like this. This is the redrawn version of diode sampling gate. This you can easily understand, make it by going through. This is, there are 4 nodes in this circuit, 1, 2, 3 and 4 nodes. So make it as this node is connecting with V0 and this node is connecting with Vs. So this is V0 node and it is Vs node. This is node A, node B. So simply add the elements which are present between these nodes. Between A and V0, what is that? This is D1. D1 is connected between A and V0, and while drawing the diode symbol, P side of the diode is connected with A. So you must ensure diode 1, P side should be connected to A and N side should be connected to V0. Similarly for D2, okay, D2 is between V0 and node B, and P side of D2 is connecting to V0 and N side of diode is connecting to node B. So that is what ensured. This is okay now. Okay, and now next come for the others. That is between A and Vs. Between A and Vs there is a resistor called as R2. Okay, and next between B and Vs there is a resistor called as R2. This is, so this one is over, this one is over, and Vs is this one. Next the remaining is nothing but control voltage. Control voltages are going to be connecting to node A. Node A is connecting with a control voltage whose polarity is more positive, and for B the polarity is going to be minus plus, so you must mention this minus plus. Okay, so this is what the diagram, and output voltage always across RL, so we have mentioned output voltage also. Okay, this is equivalent circuit. From this one we are going to draw the Thevenin's equivalent circuit for this one. Look at this. So we are going with diode 1 is connecting with V0. That V0 I have taken over here, RL, which is connecting to ground, and this is what D2. So what I am interested is, now I am going to apply VTH equivalent voltage across N side of D2, equivalent voltage across P side of D1. So what is the equivalent voltage? Instead of drawing a bigger circuit, now I am going to apply, okay, Thevenin's equivalent circuit when you are looking out of P side of D1, Thevenin's equivalent circuit when you are looking out of N side of diode. So that means if you are looking into this side, what is going to be the equivalent circuits? Okay, that entire circuit is replacing with Thevenin's equivalent. Okay, so by that time, if you are looking into this side, now consider this side. So from this point to ground only you are considering. So from this point to ground you can also go in this way also. This is also ground. So what is the effective voltage across this point and ground? That is called as Thevenin's equivalent voltage, and effective resistance across these two nodes is treated as Thevenin's resistance. Since it consisting of two voltages, one is Vc and one is Vs, we will consider one voltage at a time. Okay, using superposition theorem we will calculate the equivalent voltage. So first we will consider Vs. Okay, Vs is not equal to 0 and Vc is 0. Then voltage across A due to Vs is going to be Va. Yes, we will go with S suffix is nothing but with respect to source signal. VAS, voltage at node A with respect to source signal. Okay, so by that time it looks like, yeah, you are going with some Vs voltage, and that Vs voltage is going to be applied across two resistors, and one is RC, the other is R1, and voltage across this one is nothing but VA. So VA is nothing but voltage from node A to ground. Since Vc is grounded, this will be simply replaced with short circuit. Superposition theorem, when we are considering Vs is Vs, Vc has to be grounded. So that means voltage across node A means Rc divided by R1 plus R2 into Vs. You can write it as Rc divided by Rc plus R2 into Vs. So assume that this combination Rc by Rc plus R2 as alpha Vs. So simply let Rc by Rc plus R2 as alpha. Okay, instead of writing that much bigger, I am going to make it as alpha. Next case is Vs is equal to 0, Vc not equal to 0. By that time, what is Va, node voltage at A with respect to control signal? Now we consider Vc is present and Vs is equal to 0. That means it is connected to ground. So now it looks like Vc you are applying and that has been connected across two resistors, and Vs is grounded. This is R2 and it is Rc. Node A is voltage from node A to ground. So this is the voltage. Voltage drop across R2 is now VA due to control voltage. So this will be equal to R2 divided by Rc plus R2 into Vs. So R2 by Rc plus R2 can be written as, okay, VAC is equal to 1 minus alpha. Alpha means Rc by Rc plus R2, so replace that one. Then you will get this term. R2 by Rc plus R2 can be written as 1 minus alpha when alpha is Rc by Rc plus R2 into Vs. And third point is equivalent resistance. While calculating equivalent resistance, we must place both the voltages has to be grounded. So both voltages are going to be grounded. Then you are looking into node A. So from this one, this is node A. A is going to be connecting to ground through Rc as well as through R2. So equivalent resistance is going to be R2 parallel Rc. Now we can draw equivalent resistance as R2 parallel Rc, that I am assuming it as R1. Let or say R1 is equal to Rc parallel R2. So this is equivalent resistance across node A, and it consisting of equivalent voltage as two voltage sources. Okay, one is plus minus, the other is also plus minus. One is alpha Vs, the other is 1 minus alpha times of Vc. Since the circuit is going to be symmetrical, only the polarity of Vc gets differed. Okay, so diode 2 can also be written with the same way. That is R1, which is value is Rc parallel R2. Next it will be connecting with alpha Vs with plus minus. Later it is minus plus with 1 minus alpha times of Vc. So this is Thevenin's equivalent applying across both sides of the diode. Now the circuit has become simplified. We can able to calculate gain. So in the latter stage I am going to replace diode with equivalent model, that is nothing but a resistor and voltage combination, piecewise linear model of diode. It's a simple diode. The diode can be replaced with, okay, diode can be replaced with its forward resistance along with cut-in voltage. So this is V gamma and it is RF. We assume that both diodes are going to be of identical nature, so both can be replaced with RF and V gamma. Okay, if you are replacing, then this RF and R1 will be in series. Here also this RF and R1 will be in series. So you can replace both the resistors with single resistor, that I am assuming it as R3. R3 is R1 plus RF and with voltage source V gamma along with these two voltage sources. And this V gamma is going to be very small, you can assume. Otherwise you can also consider that V gamma also. Now we will see how to calculate V gamma, gain. So these are the three things we have taken. R1 means R2 parallel Rc, R3 means R1 plus Rf, okay, and alpha is Rc by R2 plus Rc. This is equivalent circuits for the bidirectional diode gates when diodes are replaced with their piecewise linear models. Okay, and we already checked this one. If no input signal is going to be applied during transmission period, okay, during transmission period, if no input signal is applied, V0 is equal to 0 when Vs is equal to 0 during transmission period. That is, when the diodes are forward bias, V0 is equal to 0, it is independent of control voltage, as the control voltage is going to be applied with same polarity and both are going to be insisting on the same node, one with positive voltage, one with equivalent negative voltage. So effective voltage at the output is 0 when the input signal is 0 during transmission period. Okay, so that's why we can consider it as V0 is only function of Vs. Voltage across V0 is only decided by Vs itself. Remember that one. But you may think that one, what about this V gamma? Okay, V gamma also, if you check, this is plus minus. This is plus minus. Now node P, that is output node. Output node is going to be connecting with negative polarity of V gamma with respect to D1 and positive polarity of D2 with positive polarity of the diode with respect to D2. That is, again the cut-in voltages are going to be applied in equal amount but in opposite direction. So they will also doesn't affect the outputs. So no need to consider this V gamma during transmission period. No need to consider this Vc during transmission period, because both are going to be same in magnitude but opposite in direction, so they don't have any effect, okay, at the output voltage when Vs is equal to 0. So V0 is only function of Vs. So V0 is only function of Vs during transmission period. Okay, so from that one we are going to draw the Thevenin's equivalent circuit across output terminals RL. That means like this. Across RL I am going to apply Thevenin's equivalent. So I am going to write this is RTh and it is VTh. So what can be the value of RTh? What can be the value of VTh when you are going to looking at this point? VTh can be directly written as alpha times of Vs. VTh can be written as directly V0 is equal to alpha times of Vs. Okay, because this is not having any effect, so it can be replaced with a short circuit. This also can be replaced with a short circuit. By that time the node voltage is going to be exactly equal to alpha Vs at any point of time. Okay, with respect to this parallel path, with respect to this parallel path, it is treated as alpha Vs. So VTh is equal to alpha Vs. So you can replace it as alpha Vs. Next, okay, RTh. RTh is nothing but you are going to look at these two nodes. Then these two are in parallel. That is, this branch and this branch is in parallel. So R3 and R3 are in parallel. So RTh can be written as RTh is going to be R3 parallel R3. Since both are going to be same, resistance will be get half. RTh is equal to Rs by 2, R3 by 2. So this is equivalent model. This is the circuit. Alpha Vs is the Thevenin's voltage and R3 by 2 is the Thevenin's resistance. Okay, R3 by 2 is the Thevenin's resistance, alpha Vs is Thevenin's voltage, and this is V0. So now we can easily find the gain relation. V0 is equal to, using voltage division rule, V0 can be written as alpha times of Vs into RL by RL plus R3 by 2, and gain is equal to V0 by Vs. So take this Vs this side, then it will be alpha times of RL by RL plus R3 by 2, which alpha can be replaced RC by RC plus R2. So this is the gain of the circuit. Gain of bidirectional diode sampling gates. Now we will see how to calculate Vc minimum and Vc maximum, Vc minimum and Vn minimum. Okay. Okay, look at this one. So this is simply a diode 1 and it is diode 2. Both are forward bias. If no voltage is going to be applied, okay, if no input voltage is applied, then diode 1 and diode 2 are forward biased by same amount. Remember that one. Okay, so that output voltage is 0. But what happens as okay Vs is applied? Now we are going to consider Vs is applied. When Vs is applied, assume Vs is positive going signal. Positive going signal. That means Vs is more positive. As you are applying Vs is more positive, this is the diode which is like this, and this is the diode which is in this manner. Okay. So Vs is more positive signal. You are applying more positive voltage. For example, alpha Vs, say it as plus 2 volts you are applying and plus 2 volts you are applying. Before applying plus 2 volts, both the diodes are forward biased by the same amount. But now, as you are applying plus 2 volts and plus 2 volts, this plus 2 volts you are connecting towards P terminal of the diode 1, and this plus 2 volts you are applying towards N side, N terminal of the diode 2. That means D1 is more forward bias and D2 is less forward bias. Forward bias across D2 is reducing and forward bias across D1 is increasing. So forward bias of D1 increases and forward bias of D2 is going to be reduces. As Vs is going to be increases at one point, D1 is more forward bias. Okay, D1 is more forward bias, but D2 may come into reverse bias. So at this point, okay, you must stop where this doesn't act as bidirectional sampling gate at this point. So you can apply Vs. You can apply Vs such that just it is going into verge of diode 2 becomes reverse bias. The same is going to be true whenever you are going with a Vs as negative going signal. By that time, forward bias across D1 reduces, forward bias across D2 increases. Okay, at an instant when the D1 becomes reverse bias, that is the limit where it can act as bidirectional sampling gate. So we assume that one. This is we assume that one. We are going with the minimum control voltage. We assume that one, the minimum control voltage for the application of Vs, that makes diode D2 reverse bias and diode D1 forward bias. Just it enters into reverse bias. That is at the verge of forward bias, it is going into reverse bias. Okay. So for this, what is the control voltage? What is the control voltage? Okay. For what control voltage and for the given Vs, the diode 1 is going to be forward bias and diode 2 just enters into reverse bias. Okay. By that time, the voltage across output node is going to be same. So you can calculate V0 with respect to diode 1 forward bias, and you can also calculate diode V0 with respect to diode 2 reverse bias since it just entered, and you can equate both the voltages to get the relation for the Vc. Now write the equation for V0 with respect to D1 forward bias. Whenever D1 is forward bias, a current flows. Okay, so that the current is going to be dropping across R3 as well as RL, and this is the total voltage. So total voltage is dropping across R3 and RL using voltage division rule. You can write it as RL divided by RL plus R3 into, what is the total voltage? Total voltage is alpha Vs plus 1 minus alpha times of Vc, that is equal to, Okay, this is we are going with capital Vc, that is some constant voltage during transmission period is equal to, and now there is no current flows since diode enters into reverse bias, so that no current flows. Whenever no current flows, there will be no voltage drop across R3. So voltage across output with respect to D2 is equal to this sum of these two voltages, that is alpha Vs minus of 1 minus alpha into Vc. So simplify this voltage, simplify this one, you are going to get the voltage Vc minimum. Vc minimum is equal to Rc by R2, Rc by R2 into R3 by R3 plus 2RL into Vs. So the minimum value of control voltage during transmission period should be equal to this much, so that both the diodes are going to be forward bias, so it can act as bidirectional sampling gate. If the minimum control voltage is lesser than this value, then diode D2 becomes reverse bias and diode D1 becomes diode D2 becomes reverse bias for the positive going signals, and for negative going signals diode 1 will become reverse bias, where it cannot act as bidirectional sampling gates. So now we will see how to calculate Vn minimum. Vn minimum, that is what is the minimum amount of voltage to be applied so that both the diodes are in reverse bias. Okay, so the diode is going to be looking in this direction, and here the diode direction is this way. So now, if this is the case, how can we go through this? D1 is reverse bias, D2 is reverse bias, so you can draw like this. The equivalent circuit is nothing but here you are going with R3, that is R1, okay, and diode is replacing with open circuits, diode 1, and later it is going with RL, and diode 2 is acting as open circuit. There is no forward resistance RF since it is reverse bias, so we are only considering R1 only, okay, and afterwards it is connecting with R1, and later these are the two voltage sources, and here also these are the two voltage sources we are considering. This is D1 reverse bias and it is D2 reverse bias, okay, and remember that one we are only going with positive polarities. For which diode you are applying positive polarity, that only we are considering. So this will be alpha Vs plus minus, and this is 1 minus alpha times of Vn, you can write it as plus minus, and this is plus minus alpha Vs, this will be 1 minus alpha times of minus Vn. We are not going with this one, because diode 1 is connecting with negative polarity, diode 2 is connecting with positive polarity, okay. So we are only considering this loop, so from KVL across diode D2, because D2 is given with positive polarity of Vn, so for D2 you can say it as Vd plus minus voltage across diode D2, Vd is equal to okay, so write this one, Vd is equal to minus, okay, minus Vd, this is minus alpha Vs minus 1 minus alpha times of Vn. So the worst case condition is nothing but it may enter into forward bias. So worst case condition is, you may get a doubt, what happens to V0, voltage across RL? Whenever both the diodes are reverse biased, there is no current flows into RL, so voltage drop across RL is 0. So I am not considered that one. Worst case is nothing but the D1 or D2 may be coming into forward bias. By that time Vd can be treated as 0 volts at the verge of reverse bias. Worst case condition is nothing but both are reverse bias. Under reverse bias, diodes maintain some negative voltage. But the worst case is nothing but they may come towards forward bias. So verge of reverse bias or entry point of forward bias is going to be with 0 volts. So replace this Vd with 0. So 0 is equal to minus alpha Vs minus this is minus plus. This is minus plus, so you can write it as this is plus. This is plus minus. Okay, minus plus. Polarities will be same, but Vn is positive, Vn is negative over here. So minus Vs plus 1 minus alpha times of Vn. So 1 minus alpha times of Vn is equal to alpha Vs and Vn minimum. Now this is Vn minimum is equal to alpha divided by 1 minus alpha times of Vs. So Vn minimum is equal to alpha divided by 1 minus alpha times of Vs. So these are the limiting voltages. Minimum voltage to be applied when the diodes are reverse bias. Okay, this much positive voltage you must towards diode and the same amount of voltage you must apply towards diode D1 in negative magnitude. So this is the positive voltage to be applied towards D2 and the same amount of negative voltage to be applied towards D1, so that both the diodes are under reverse bias. Otherwise one may be coming out of reverse bias, it may enter into forward bias where it won't act as bidirectional sampling gate. So for a bidirectional sampling gate using diodes, we have seen the operation as well as calculation of gain and calculation of Vc minimum and Vn minimum, that is minimum positive voltage to be applied during transmission period, minimum positive voltage to be applied during non-transmission period. Okay. So now we will discuss about disadvantage of bidirectional diode sampling gates. We have calculated 3 parameters. First one is gain, the other one is nothing but minimum control voltage to be applied to make the diodes forward bias, and minimum control voltage to be applied to keep the diodes reverse bias. Okay. All these things we have done with the assumption that voltage, control voltage are going to be exactly opposite of each other. So at the instant whenever it is changing from, if the control voltage is going to be of this nature, then you are going to be getting in the opposite half. And the magnitude over here, if it is Vc and Vn, then this must be of Vn and Vc. Okay, we have taken in this way. This is minus Vn Vc and it is Vn minus Vc. Control voltages are going to be exactly opposite of each other, and that too they are changing at the same instant, but it is not practically true. So during transmission period we assume that these control voltage doesn't have any effect at the output, okay, because they are ideal control signals. They change exactly at the same time and they will maintain the same voltages in opposite direction. But it is not the case. If they are not synchronized, then the output is going to be getting deferred. Okay, so output will be deviates from its ideal value. So whatever we have calculated gain A, you don't get this one, you will get either more than this one or less than this one. So first one is nothing but output V0 during transmission period. During transmission period is sensitive to control voltage imbalance. So if they are not in balance, then definitely output is going to be gets modified. Okay, so V0 during transmission period is sensitive to control voltage imbalance. This is first disadvantage. And second disadvantage is gain is very low. Gain is very low because gain equation is RC by RC plus R2. So definitely this is going to be yielding less than 1 multiplying with this value. This value is also less than 1. So the gain is going to be very less. So that is gain is very small. Generally we expect ideally, okay, since diodes doesn't amplify, we expect at least V0 is at most V0 is equal to Vs. Okay, V0 should be equal to Vs. Since diode cannot give amplification, so we should go for a circuit which gives V0 is equal to Vs. But this circuit is going to be giving very less gain. And third case also, if you see, third case is Vn minimum. Vn minimum value is RC divided by R3. Okay, where R3 is equal to R1 plus Rf, and R1 is equal to R2 parallel with RC plus Rf. And if you observe, R2 is going to be very small compared to RC, and the R2 is smaller than RC, so that this value is going to be very much lesser than R2, okay, plus Rf. The value itself is going to be less than R2. Okay, the R3 value is going to be less than R2, but RC is greater than R2. Vn minimum is going to be greater than Vs. Whatever the signal you are applying, more than that one you are applying as minimum voltage. And Vc minimum is going to be something lesser than Vs. Okay, Vc minimum during transmission period you should apply less voltage compared to Vs, whereas during non-transmission period you are applying more than the source voltage to keep the both diodes reverse bias. That's the disadvantage. Vn minimum is going to be greater than Vc minimum. Vn minimum is greater than Vc minimum. Okay, that is, to keep the diodes reverse bias you are applying more voltage. To keep the diodes forward bias you are applying less voltage. Okay, so this is also treated as a disadvantage. And fourth disadvantage, whenever during the diodes are reverse bias, there is nothing but they are acting as open circuit. When they are acting as open circuit, we expect like this. Open circuit. But whenever the signal voltage, if you are applying a high frequency signal, for high frequency signal diode gives some capacitance across the terminals. When they are in reverse bias, at that time that capacitance is called as transition capacitance. So now it will be equivalent to this circuit. So output is now coupled to Vs through capacitor resistor network. Okay, at high frequencies diodes find capacitance, internal capacitance, that too of type diffusion capacitance under forward bias and transition capacitance under reverse bias. Under reverse bias we expect V0 is equal to 0. It is not function of Vs, but if the Vs is high frequency signal, then the diodes is going to be finding some transition capacitance, so V0 may be related to Vs. Okay, even during non-transmission period. So there may be appreciable leakage through diode capacitance. So because of leakage you may get some output during non-transmission period. That is fourth disadvantage. Fourth disadvantage is there may be appreciable leakage through the diode capacitance at high frequency signal, at high frequency inputs. Okay, these are the four disadvantages. Next we will see how to overcome one by one. That is, first one, how to overcome. That is, V0 should be independent of control voltage. How to make this one. And next, how to make gain is equal to approximately equal to 1. Anyhow 3 and 4 are going to be not modified, so we will concentrate on 1 and 2 disadvantages in the next class.